Hello, everybody. It's 5 p.m. according to my computer clock. This is the International Space Science Institute's Game Changer seminar series, where we look at missions that changed the game in the space sciences. I'm Tilman Schwan, and I'm your host again today at ICI in Bern. Today we have Rudolf von Steiger, who's been your host the past seminars, speaking himself about Ulysses, the ESA mission to first Jupiter and then on to the Sun, and then orbiting the Sun on an almost polar orbit. Today's seminar will actually be the last one on the Sun and the solar wind for now, at least. And after a pause of a week, next week, we will turn to astronomy and astrophysics missions with the first talk by Enrico Bozzo on Integral on November the 5th. But now, today it's Rudi, who is a director at ISI and a professor at the University of Bern. He is a co-investigator of the solar wind ion composition experiment on the mission of Ulysses, and associated scientist of the EMPTY, ACE, and solar orbiter missions. He's a theoretician modeling the solar atmosphere, as well as analyzing and interpreting observations of the solar wind, both in the Earth's magnetosheath and in interplanetary space. Well, without further ado, Rudi, thanks a lot for joining us today, and the floor is yours.
Thank you, Tilman, and good evening, everybody. Thanks for joining in. And let me share my screen now with my presentation about Ulysses, a new perspective from High Latitudes. Ulysses is a mission that has a long history. I will first talk a little bit about the genesis. In a second step, present a few selected results and say something in the third part about the end of the mission and its successors. And like a brontosaur, this is thin in the beginning, thick in the middle, and thin in the end again, with kudos to Monty Python. So let's start with the genesis of the Ulysses mission. The beginning of the Ulysses mission actually, I think, should be traced back to the late Giuseppe called Bepi Colombo. As we know from the mission which bears its name and is on the way to Mercury, Bepi Colombo discovered or found that orbits of spacecraft can be significantly altered by gravity assists from planets in the solar system. And that led ESA, or the precursor of ESA, ESRO, the European Space Research Organization, together with NASA, to conduct a feasibility study for a mission over the poles of the Sun, then called ISPM, International Solar Polar Mission. The idea was to send two spacecraft out to Jupiter, and why Jupiter you will see in a few minutes, and with flybys in the neighborhood of Jupiter, deflect their orbits so they would be sent on nearly polar orbits over the poles of the Sun, counter-rotating one way and the other, the two spacecraft. Of course, avoiding to crash each other, but space is big enough, don't worry about that. The NASA spacecraft would have even included a coronagraph for optical observations and other telescope for optical observations of the Sun. But alas, in 1981, these were the Star Wars years. NASA, or the Congress rather, shifted the budget around, and NASA pulled out of the MOU and canceled its spacecraft. And it was only due to the foresight and the force of then ESA Science Director Roger Bonnet that the European part of the mission could be saved, and it was saved under a new name, Ulysses. The Ulysses mission continued to be an ESA-NASA collaboration, and it was named after Dante's hero in Divina Commedia, not after the Homerian hero, but after Dante's hero, who was described in the Divina Commedia as the man who visited the land beyond the sun. A very fitting name for the mission. The ESA part of the mission was the design and the construction of the spacecraft. ESA, or rather the ESA member states, contributed half of the instruments. ESA would integrate them, and ESA conducted the mission operations with a team based at JPL. On the other hand, NASA would contribute the shuttle launch planned for 1986, the power supply with a radiothermal generator, not available to European technology. The other half of the instruments, and the communication using the Deep Space Network. This is Ulysses, nicely golden wrapped. It was a rotating spacecraft with a rotation axis in the direction of the telemetry dish, and which always had to point at the Earth. This is a shuttle. I'm not sure which one. Oh, actually, it's two. I'm only seeing that now, which would be used for launching the Ulysses mission. But then the problems started. In January '86, on the launch of the Challenger, before it would have to have carried Ulysses, it exploded on the launch, a big disaster, which necessarily led to not only a launch delay, but it also had a consequence that the inertial upper stage, which was needed for Ulysses to inject it once it was launched in low Earth orbit on the Challenger, to inject it onto an orbit to Jupiter, had to be converted from liquid to solid fuel. Just imagine how the Challenger disaster would have ended with a liquid inertial upper stage in the cargo bay. Yeah, I think it was disastrous enough, but this was no longer possible. And as another consequence, the same had to be done for Galileo, which was also scheduled to go to Jupiter. And because Galileo needed to get into orbit at Jupiter, unlike Ulysses, with an inertial upper stage, which was weaker, only solid, not liquid fuel, it had to use gravity assists, Bepi Colombo, also at Earth and other smaller planets, in order to arrive at Jupiter so it could be injected. And because that journey took longer, Galileo received an earlier launch slot in '89 than Ulysses, which was could only be launched in 1990. Nevertheless, Ulysses arrived before Galileo because Ulysses just had to fly by Jupiter. Once Ulysses was launched successfully and injected into the orbit to Jupiter, another problem began, and Ulysses started to nutate. This is a very bad movie of Ulysses rotating around the axis of the communication dish. And at the opposite side, you see it here, there's an axial boom. And this axial boom caused a problem because the axis is directed at Earth. And if the angle between Earth and Sun is appreciable, then this boom was sunlit. And because it was made of two shells, it was sunlit for 6 seconds on the one side and for another 6 seconds on the other. And oops, too fast, not too fast. And I just start the movie down here. What that caused was a nutation of the spacecraft with the effect that the axis would slowly deviate from the direction to Earth. And if it deviates for more than the blue circle here, the communication would have been lost. The spacecraft operation team devised an ingenious method firing thrusters at just the right time to keep that axis in the direction of Earth. And thankfully, this scheme was devised in time, so Ulysses was not lost before it could even be switched on and commissioned. Now these problems were behind us. Ulysses was safely on an orbit to Jupiter. I'm not going to say much about the ecliptic part of the Ulysses mission, but only say something about the Jupiter flyby. Ulysses flew by Jupiter quite closely, and the effect of a flyby is summarized in this formula, that the angle or half the angle is given by this formula, which includes the mass of the planet, of which Jupiter has a big one, so that's good because it's in the numerator, the relative velocity in the denominator, and the impact parameter. As small as possible impact parameter is a good thing because that deflects the spacecraft the more, and the smaller velocity also is a good thing because that increases the deflection angle. If you evaluate that, what it boils down to is that the escape velocity at the point of closest approach square needs to be bigger than the planetary orbital velocity twice the planetary orbital velocity squared. And that is very well fulfilled at Jupiter, where the escape velocity is 60 and the orbital velocity is something like 13 kilometers per second. Now, of course, admittedly, Ulysses did not go down to the surface of Jupiter. So the escape velocity at closest approach was not 60, but it was much more than the planetary orbital velocity. Ulysses went inside the plasma torus of the Io of the innermost of the 4 Galilean moons. With this, Ulysses achieved an orbit inclination of the order of almost 80 degrees relative to the ecliptic and the solar equator. So Ulysses was safely injected in the polar orbit. Here you are. First orbit, these are the orbital parameters, 6 years orbital period, and here angles and eccentricities and all that for the astronomers. First time around, second time around, and almost a third time around in the early 2000s until 2008 and then 2009. I will return to that point at the very end of this talk, when Ulysses had to be switched off. These were the 3 polar orbits, almost completed 3 polar orbits that Ulysses performed. With this, I come to the results. Now, Ulysses has given us a wealth of results, and I can present here a selection which is biased by my own knowledge and even more so by my own ignorance of some of the results. So it will be a subjective selection, and I apologize upfront to everyone who might not be represented here. So, but I'll try to give a tour d'horizon of some of the results. Look here at the list of the sensors on Ulysses. Ulysses, unfortunately, because of the NASA pullout from the MOU, did not have any optical instruments. So unlike Daniel Müller 3 weeks ago, I'm a bit, I can't show you nice pictures, but I'll try to make up with the results that the Ulysses gave us. A small payload of a little more than 50 kilo, using a little more than 50 watts. And look at this, talking to the Earth with less than a kilobit per second. That's a very slow talker. Now you can imagine, even if had there been an optical telescope, bringing down the data would probably have hogged all other instruments, and we would have nice pictures, but nothing else. So let me talk to you about the else part of what we got from Ulysses. Here's the instruments on the deck of the spacecraft. Power supply of the spacecraft here in the back, radio thermal generator, sufficient power for more than just a nominal mission, which would have ended after the first set of polar passes and was faithful and useful for almost 3 complete solar orbits. A dust instrument, radio plasma waves, interstellar gas. I will show a plot of that. Here is our instrument, the solar wind ion composition spectrometer. Here's the plasma instrument. COSPIN was a cosmic ray instrument. High scale was an low energetic particles instrument. And on the radial boom, there are the magnetometers and the gamma ray burst instrument and the radio plasma waves again. So that's the Ulysses instrument suite. And let's look into a few of the results, which are summarized in several books. Here, a solar minimum book, a solar maximum book, oops, too fast, sorry, and Heliosphere throughout the solar activity cycle. All of these books are recommended in case you need or wish to hear more information on anything which I either leave out or skip over in this talk. Now, the first orbit was completed during a minimum phase of the solar cycle, when the sun was at minimal or declining to minimal activity. That is a fortuitous consequence of the delay which Ulysses suffered for various reasons: Challenger accident, Galileo preference, and others. Because had it been launched a few years earlier, this picture, which I think is the icon of the first Ulysses orbit, would have looked much more confusing and different. Look at this nice and fairly simple picture. It appeared on the cover of GRL. What's pictured here, just look at the graphics first. The picture, as said before, is not Ulysses, but SOHO, EIT, and LASCO, together with Mauna Kea coronagraph. What Ulysses found going out from the ecliptic at Jupiter, going first south, was a variable solar wind, fast and slow, with mixed magnetic polarity. The magnetic polarity is given here in red for outward and in blue for inward, with mixed polarity. And then there started a very interesting period with alternating fast and slow streams. I come back to that in terms of composition, until quite, I think it's fair to say, unexpectedly, Ulysses entered a uniform fast stream for almost all, or more than half, of the southern hemisphere, which continued on the fast latitude scan. Remember, this aphelion was at 5 and more AU, perihelion is at 1 AU, so this half was traversed much faster than the other half. After traversing the low latitude region, Ulysses came back again into a unipolar, uniform stream over the north polar coronal hole with outward interplanetary magnetic field, and all the way down to the ecliptic plane after 6 or so years after the first orbit. A very simple and very clear picture of the heliosphere. The fast streams were immediately, of course, associated with the coronal holes, which you see very nicely in this EIT picture here underneath, the coronal holes, and the slow and variable solar wind, which we already knew very well from observing it with Earth with spacecraft close to Earth near the ecliptic for decades before. That part we knew already very well, but there's a new type. It was not exactly new. Fast solar wind streams were very well known, but there's this uniform polar magnetically uniform stream of almost structureless solar wind over the poles. And that's, in a nutshell, the summary of the first orbit in plasma and magnetic field. This led, one more point here, the last bullet. No, two more points first. Look at the coronal holes in the EIT picture. Their extent, their angular extent is less than the angular extent of the fast stream. So there's super radial expansion of the fast streams from the polar coronal holes. And number two, a small side point, if you are worried about the wrong polarities here and there, a few blue points or here or a few red points here, these are not really inverted polarities. These are inverted magnetic field lines due to interplanetary and other interactions, and they were shown in a nice paper by Geza Erdős to be apparent. The polar streams is actually unipolar in magnetic field, inward and outward. This has led Fisk to theorize, based on the two assumptions, A, superradial expansion, and B, differential rotation of the sun. He came up with a magnetic field model, which is today called the Fisk model, and which is summarized in these three plots that I borrowed from his '96 paper. Here you have the polar coronal hole with the open magnetic field, which super radially expands. The polar coronal hole is not sitting central on the rotation axis. Magnetic axis is always a bit tilted relative to the rotation axis of the sun here. And it expands super radially to these theta prime angles and fills a larger part of the solid angle over the sun than the coronal hole fills. A consequence of that from the differential rotation is that magnetic field lines, these magnetic field lines rooted at the sun, migrate in a pattern which is depicted here, migrate across the coronal hole. And that leads to a very intriguing and interesting and fundamental consequence, namely that the magnetic field lines, which would simply, picture B, which would simply follow these spirals if the sun were to rotate in a purely Parker type field. A purely Parker type field of the solid rotating sun would simply have such magnetic field lines. Not so in the Fisk model. The transverse components of the magnetic field at the high latitudes is much, much more increased relative to the simple Parker model. And that has enormous consequences, as especially also for cosmic rays, as we will see in a minute. The Fisk model was further elaborated together with Thomas Zurbuchen and Nathan Schwadron. And in the end, it came to this picture here of the migrating field lines across the polar coronal holes, which would then work their way in the streamer belt, along the streamer belt with reconnection events, like walking from one reconnection event to the next, opening up one loop after the next, back to the other side in order to start their migration. Again, that's the Fisk model. It is, it has been much discussed. I hope I have presented it as best as I can, but the consequence of the Fisk model is this migration in the streamer belt in order to start their migration across the coronal holes. Again, that was an early theoretical prediction from the Ulysses mission, even before or maybe after the first orbit was complete. When you have the two types of solar wind, fast streams alternating with slow solar wind, these two interact and lead to corotating interaction regions, as depicted here, especially when the magnetic axis of the sun is somewhat tilted. This leads to a current sheet, the current sheet, the sheet between the north and the south polar magnetic polarity. This leads to a current sheet which is tilted, and if the tilted current sheet rotates, that leads to this wavy current sheet of which was depicted here in this nice paper of Gosling and Pizzo. This can be tested observationally. In the same paper, they depicted here how the part of where the slow solar wind emerges over the streamer belt is tilted relative to the rotation axis, fast solar wind north and the south. That leads to these interaction regions here, far from the sun, the corotating interaction regions. And these interaction regions would create waves. The waves would then steepen up gradually to develop shocks, exactly like on the right-hand side here. Art Hundhausen had predicted decades before. You can see here how this fast stream creates an interaction region. A forward wave develops into a forward shock, and the reverse wave develops into a reverse shock. And the point of the Gosling paper was that these reverse shocks would travel poleward, whereas the forward shocks would travel equatorward, and that can be tested and has been tested here. And as you can see, at low latitudes, in the middle of the plot, low latitudes, you have forward shocks and reverse shocks alternating more or less in equal numbers, but the higher you come in latitude, the reverse shocks are more dominant. They travel further to higher latitudes, exactly as predicted by this picture. Next is a consequence from the Fisk model about the cosmic ray modulation. I remember one of my first international meetings in the late 80s when I first met with cosmic ray people from the Ulysses and other missions, that they were very much looking forward to the launch of the Ulysses mission, because that would give them access to the undisturbed interstellar cosmic ray spectrum, because the cosmic rays would be able to access the high latitude portions of the heliosphere much more easily than they can in the equator. Remember the wavy current sheet, the cosmic rays have a very hard time coming into the inner heliosphere across that wavy current sheet. From the poles, the access was presumed to be much easier, but as Edgar Page put it in the encyclopedia, the long postulated increase in cosmic ray flux over the solar poles was not found, period. And the large magnetic field fluctuations, Enterle, Fisk, seen almost continuously in the polar regions, invalidated the concept of easy charged particle access along smooth radial field lines, the Parker field lines, which I showed earlier. Now, that's not to say that Ulysses was a failure for cosmic ray instrument. Ulysses, together with the Voyagers and together with all other cosmic ray missions, has contributed tremendously, but I'm not the cosmic ray scientist, and for this reason, I'm going to leave the cosmic rays here and now. Again, sorry about that. Second orbit. Now that's a completely different picture. 98 Ulysses was, again, had completed its first orbit. Jupiter was on the other side of its orbit. So by the way, no danger of running into Jupiter again. And then solar activity picked up and we got a second orbit. And during that second orbit, what you see is altogether totally different. Had we received that orbit before the first one, I think our colleagues would have said, well, why do you go to high latitudes? Everything looks the same as it does at low latitudes. Ulysses was a complete waste. And only if once we would have seen that picture, we could have rehabilitated ourselves. The second orbit at high latitudes was equally interesting, but at high solar activity, it did not look much different from the first orbit. That is to say, there is something like a polar coronal hole here, but it was not very long lasting. There were coronal holes all along, also during solar maximum. They are distributed all over, can be distributed all over. They're not exactly equal to the large polar coronal holes at solar minimum, but sufficiently so. But the mixture of slow and fast solar wind was totally much more mixed up, less organized than during the first orbit. Here are two movies of how the current sheet looks. Left at solar minimum, right at solar maximum. The late Brian Grimm in Michigan created these. The current sheet here, or the current sheet looks like in one of these pizza places, pizza dough, somebody who makes a pizza and flips and the dough or just around in the air. Ulysses observes it from above and from below. The current sheet is somewhat waved here at solar minimum. It is strongly waved here at solar maximum. And you can see the two polarities with two colors. Soon we will approach the Earth. Just let's see how we're doing time. Yes. Here's the Earth coming. Oh, that should be faster. Just to give you the scale of time. And here it is. The Earth rotates at the natural rate. So you see the time scale. And the difference here is that the current sheet is much more wavy at solar maximum. The pizza baker has failed in creating a nice and flat pizza dough. And here it is. Although polarity reverses regularly, it is much flatter than that. Let's skip over the rest of this and give you two more results from the global magnetic field. Ed Smith, also a Ulysses scientist, in a 2000 paper, investigated the total open flux in the northern hemisphere and in the southern hemisphere. And from the fact that the two fluxes need to equal each other, or else the sun would carry magnetic charge, which it can't. He concluded that the solid angle in the northern hemisphere had to be larger than the solid angle in the southern hemisphere, indicating that where the current sheet was conical and deflected towards the south by something like 10 degrees. And finally, another magnetic result by Ryan Jones with Andre Balogh and Ed Smith. He investigated exactly how the magnetic polarity reverses from one to the next cycle. We'll come to that in the third polar orbit in just a minute. He could show, or they could show, that the dipolar component is more or less preserved during the entire inversion of the magnetic field. It's not so that it goes away and reforms with the other polarity, but it is so that it just topples over in an organized manner from one polarity to the opposite polarity. That's how the magnetic field reverses from the first to the third orbit. And here's the complete picture of the first three orbits. Notice that the magnetic field polarity plots in the meantime have been cleaned up to reflect the real polarity, whether outward or inward, and not just the radial component, whether it points inward or outward. Minimum, maximum orbit, and the third orbit was again in a minimum orbit with inverted polarity, obviously, and very interesting other facts, namely that the overall magnetic field strength was weaker. The whole entire solar cycle was weaker, but other than that, it was back to the more or less organized polar configuration with the large polar coronal holes. Now, let me come to the composition part. I admit that's the part I'm most familiar with, so I have the next few view graphs on composition. The ion composition instrument, the solar wind ion composition instrument with PIs George Glöckler and Johannes Geis, was in a way a game changer in and by itself. Like Ulysses, it was the first time that such an instrument was flown in the open solar wind. A very similar instrument had been flown on the AMTI mission, where I could train myself. But it stayed inside the magnetosphere, and only in small time portions when it entered the magnetosheath, it could observe shocked solar wind there and get a glimpse what Ulysses would see a few years later. This instrument was a true mass spectrometer because it was a combination of an electrostatic instrument combined with a time of flight portion, with a time of flight telescope, and a total energy measurement with solid state detectors. With these three measurements, the ions could be characterized as to their mass, charge, and energy separately. That was an absolute first in the solar wind, and it has worked beautifully thanks to the Maryland and Bern groups who conceived and constructed that instrument. What we see on the left-hand side is a graph of count rates in mass, not charge, but mass per charge, but this information is the same, where you see the ions that could be identified separately with Ulysses. Here, protons heavily suppressed and helium, because these were observed with the plasma instrument of Sam Baim and later John Phillips and Dave McComas. And here are the heavy ions, everything starting from carbon to oxygen, neon, magnesium, silicon, sulfur, and iron could be identified one ion by one and they could be separated from each other with almost certainty. The biggest peak here is oxygen 6 times charged. This one is carbon 6 times, 5 times, 4 times charged, and so on. You have something like 25, 30 different ions. And because what this picture doesn't show, you have also the energy of each one of the ions you get. You can have distribution functions, energy distribution or velocity distribution functions for all these ion species separately. That opens up a whole new box of tools with which you can analyze the solar wind with unprecedented tools. This was the picture of ions obtained in the fast streams from the South Pole on the first orbit. Now compare that to what's been observed in the ecliptic before getting there. Ions distribution, ion charge states are much different. Again, in the North Polar Pole, again, a different picture. And what's also important, a quick flashback to Jupiter encounter. At the time, it was still controversial whether the solar wind ions would be so highly charged as we found them. Oxygen almost, carbon 6 times is fully stripped. Oxygen 6 times is a helium type ion with 2 electrons left. Very highly charged. No low charge ions, but we were accused of saying, oh, your instrument is just not sensitive there. Oh yes, if there were low charge ions, as there have been during Jupiter encounter, I remember the Io torus, mainly consisting of sulfur and oxygen, we would immediately see them. Here they are, but they are not there in the solar wind. Now, as I said, that opens a whole new toolbox. Let me give you three elements of that toolbox from this overview. These ions we could measure their velocities. They all flow essentially at the same speed. Here's the speed of the alpha particles. That's nothing new compared to what the plasma instrument can measure. But the ratios of the charge states could be interpreted as a coronal temperature, as I will come to on the next view graph. The ratio of 2 of the oxygen charge states were giving a coronal temperature. And you could see that this coronal temperature in the coronal holes, remember that's between 92 or 3 up to 96, that's South Polar coronal hole, for North Polar coronal hole, are much cooler than the rest of the solar atmosphere, corona. And again, the same is true during the third polar orbit. And also the elemental abundance ratios showed a dependency on the solar wind type. Not quite as clear as the charge state temperature does, but equally important. With a superposed epoch plot of this interesting period in 92, 93, when Ulysses was alternating on its way down to the South Polar coronal hole. Fast stream from the South Polar coronal hole was an alternating period. Once every rotation of the sun, you encountered the stream and then came back into the slow solar wind. A superposed epoch analysis done together with Johannes Geiss and George Clerkley gave this view graph where you see how the speed is very nicely anti-correlated with the freezing in temperature from the oxygen charge states, and also with a ratio of, for example, magnesium to oxygen, but it could also be the iron to oxygen ratio. The charge states are indicative of the coronal temperature. Here are the charge states in 4 periods, South and North Polar coronal hole in blue and green. they are tendentially lower, as we have seen 2 view graphs ago, than in the maximum and minimum slow solar wind, where there is a prevalence of higher charge states, indicating a hotter corona there. Cool coronal holes on the one hand, hot streamers on the other. In the 2 periods of cool coronal holes, that could be used even in a science paper by Johannes Geis et al., could be used to infer a coronal temperature profile, because what establishes these charge states? It's the collisions with the hot coronal electrons and their density and the ionization recombination rates act together in a sense that with the expanding solar wind, it keeps equilibrium with the ambient hot electrons. And when the density goes down, the equilibrium gets frozen at some point, namely at the point where the expansion timescale overcomes the ionization recombination timescale. That's the freezing in process, and that point of loss of equilibrium is further down for carbon and oxygen. It's higher up for silicon and iron, and taking these charge state temperatures, that establishes a very, very, very rough coronal temperature profile. It's also worth noting that the iron charge states are follow a one single temperature. Here is a single temperature, 1.2 megakelvin corona has these iron charge state, the solid line. The dots are the observed points, and the dashed lines are 100K cooler or hotter, which indicates that the corona in the polar coronal hole has a uniform temperature. It's not a mixture of hot and cold material. Finally, the charge state composition can be used to identify CMEs, as has been done by Lepri. She uses, by Sue Lepri, she uses the average iron charge state and could show that this is a very good indicator of CME for CME identification. I have to speed up a little and say something about composition. Composition is the element ratio of whatever element X relative to oxygen. Again, bimodal distribution, as shown in the superposed epoch plot. The slow solar wind, accounted both during the maximum and the minimum solar activity, has a larger enrichment of the low Earth first ionization potential elements, the metals, magnesium, silicon, and iron, as compared to the slow solar, to the fast solar wind from the polar coronal holes. That fast solar wind has a weak, but still not negligible first ionization potential effect. This effect needs to be taken into account when talking about the solar abundances of these heavy ions. In 2 papers with Thomas Zurbuchen, we went on to devise a solar abundance for oxygen. That's a difficult measure because you need to compare the oxygen from the SWICs to the protons from the plasma instrument, with more a danger of systematics, but that has been done, and the result was that the oxygen abundance as inferred from the solar wind was higher than the latest abundances and the latest and confusing oxygen abundances which are inferred from remote sensing optical observations of the sun, which are creating problems with the latest solar models. But I'm running out of time, and that's why I skip over here. The latest work I've done with Thomas before he disappeared into NASA was to devise a solar metallicity, and that was our result when putting together all the Ulysses SWICs abundances from heavy ions. Remember, a metallicity is, for astronomers, is a content in ions, everything else except hydrogen and helium. This result I need to say 1 minute about is the only result about isotopes which you can measure with the Swiss instrument. The only isotope ratio you can measure is the one between helium-3 and helium-4. All other isotope ratios are out of reach. For that, you need an instrument like, for example, there was on SOHO. But this helium-3 to helium-4 isotope ratio was measured already by Johannes Geiss with his lunar foil in 69, but it was only in Ulysses in the 90s when this measurement became superseded, and the ratio can then be interpreted as density of the universe as a whole, as it has been depicted on the cover of one of the ISI workshop volumes on primordial nuclei. Now, I'm sorry, I run out of time. I skip over the pickup ions. I skip over the comet tail interception. I mentioned very briefly that Manfred Witte had discovered on Ulysses the interstellar neutrals, which were then much later analyzed in depth by a mission such as IBEX, and he managed with the Ulysses instrument to pinpoint the speed and direction of the interstellar medium, helium, which enters, and even the temperature and the density, which enters the heliosphere through the termination shock and is intercepted with his instrument at Ulysses. Now I come to the thin end of Ulysses. Allow me another couple of minutes for that. Ulysses was performing extremely well thanks to the mission operation teams of ESA and the Nigel Angold up until into the 18th year of the mission. Then the RTG was decaying so to a point that it was hardly possible to keep all the instruments running, and some of the instruments, such as, for example, Swiss, could not be switched off because the compensation heater which you needed when it was switched off would use more power than the instrument itself. So that was an ingenious way of dimensioning your instrument so it would always stay on. So the mission operation teams came up with a scheme to alternate the two biggest power consumers. That's on the one hand, the cold case heater keeping the hydrogen flowing, absolutely important, or else you lose orientation. And number two, the X-band communication to the Earth, that's equally important, or else you lose communication with the Earth. But they devised a scheme so they could switch off one and run the other and then alternate. And that was great. The Ulysses mission would have gained more than 1 year more, but then the cold case, then the filament broke for the X-band transmitter, and they don't like to get switched. That's known, but of course you needed to take the risk here. The filament broke, X-band was lost. Ulysses was kept alive for more than 1 year in addition, but only with S-band communication. Not much data came back. And then in the mid of 2009, it was switched off. And in the meantime, we have new missions which are stepping in the footsteps, which are following in the footsteps of Ulysses. Solar Orbiter. 3 weeks ago, Daniel Müller said much more about that. Solar Orbiter is not like Ulysses, but also using Bepi Colombo, multiple Venus flybys. Venus is much less effective for reasons as I have shown than Jupiter for deflecting spacecraft orbits, but working one time after another. Solar orbiter manages to reach 30 degrees or even more in latitude. As we have seen from Ulysses, that's not much when you talk about the heliosphere, the shape of the heliosphere, but that's a lot when you want to look at the poles of the sun, and that's exactly what solar orbiter can and Ulysses couldn't, and that's why we are all very eager to obtain pictures from the polar regions of the sun from solar orbiter. And number two, solar probe. Solar probe was launched 2 years ago already, and it's also using repeated gravity assists at Venus. Poor Venus, she will lose a lot of energy in her orbit, but I think she can manage. Parker Solar Probe has already passed its first perihelion, is about to come into its second perihelion, and one of the principal results which it obtained during its first perihelion was ubiquity of escaping what they call switchbacks. These are these kinked magnetic field lines here, these kinked magnetic field lines. You can see that in a movie, how it happens. Open magnetic field line encounters a loop, reconnects, and a kink, a switchback, escapes into the heliosphere. And that's precisely what Len Fisk predicted 20 years ago. And in a paper together with Justin Casper, he published just that theory. It's not an observation with which somebody based on which somebody comes up with a theory, but it's the other way around. It's an observation which works to confirm a 20-year-old theory of Len Fisk. I think that's a remarkable feat, and I think that's a very fitting end for this talk. And with this, I thank you very much for your attention. Apologize for the overrun in time, and ready for a few questions.
Yeah, thank you very much, Rudy. This was very fascinating. And it was also fascinating to see what, some of the NASA administrators have been concerned with before they, turned the energy to NASA. I wasn't actually quite aware of that, but, that's just my ignorance. Okay, like always, we have two channels open for questions. You can type your question into the chat channel, or you raise your hand and then Saliba will give you the mic and you can pose the question yourself. If you type into the chat channel, I will read the question to Rudy so that everybody can hear what the question is. We have a first entry here from Mujaba Akavan Tafti at the University of Michigan, who likes to know why the payload was so small in mass of the mission at 55 kilograms, and that in comparison to Juno. Now, from somebody who's more used to landers, 55 kilos is something that lander people can only dream about, but really.
I must admit, I joined the mission when it was already finished. In '89, I managed to help with the last calibrations, so I can't say very much about that. But I think at the time, considering the shuttle launch, considering the weight of the inertial upper stage, I think that was just about what was possible. I guess the American spacecraft might have had more because of the optical instrument, both in weight and power. But I would say that was what was possible at the time. It's more than 30 years ago. It was devised more than 40 years ago. Now that's a very long time, and space science has evolved and space technology has evolved in the meantime.
Okay, Lindsay Fletcher first acknowledges and thanks you for the great talk, and then asks the question, what is the explanation for the increase and then decrease of the electron temperature with distance from the sun?
The increase in the corona, let me see. The decrease is adiabatic expansion. I think that's all there is to it. And the increase in the corona, I'm not sure if I understand the question correctly. What?
Okay, maybe Lindsay can type a clarification into the chat channel, or raise the hand and we give you the microphone. That is it at the moment in the chat channel. I have a question. You do a lot of work on the solar composition, and for us from the planetary side, the solar composition is a reference composition that we use in comparing the compositions of planets and so forth with. Now, did Ulysses fundamentally change this? So what was the effect on our understanding of the solar composition, before and after Ulysses?
Yes, I think that's a very good question, and that's I think the jury on that is still out. What I was a bit short in presenting is two things. The first one is the solar metallicity, which putting together all the heavy ions, when done from Ulysses, comes out like a solar metallicity in the 80s or 90s, when solar models and solar abundances were still very much in agreement with each other. In the meantime, the solar guys have revised their abundances, in particular of oxygen, but also of the other CNO elements. So there is now a tension between the solar models and the solar abundances. The tension coming from there, because the solar model needs the opacities in order to keep the model running, in order to keep the model in agreement with the observation. And this opacity goes down when you lower the abundance of oxygen, carbon, and nitrogen. So one escape was that the solar guys said, oh, there could be much more neon in the sun. You don't see the neon in the sun because there are no lines which are excited at photospheric temperatures. The solar neon abundance is essentially unknown. And that's why these solar guys thought, well, we can just tune the neon up and the solar models are in agreement again. But then comes our abundance observations in the solar wind. And there we have the neon. We have a very good handle on the CNO group. We have a very good handle on the neon. Now, yes, there can be fractionation between the sun and the solar wind, but we have tried to show that in the fast solar wind from Coronal host, this fractionation is minimal. We have given uncertainties, and we think that the solar metallicity is as high as it used to be in times of the Anderson-Graves standard abundance tables, and not as low as modern Asplund solar abundances claim to be. Now, it's hard to be taken seriously by these guys because they think you're out in the solar wind and don't know nothing about the sun. But yeah, I think it's still an open issue. And I maintain that the solar metallicity is probably higher than the latest remote sensing observations claim it to be.
Okay, thank you. Now, Lindsay is on the line.
Lindsay.
Yeah, hello.
Hi, Lindsay.
Can you hear me?
Yes.
Okay, great. Thanks for the talk. I'm sorry if I wasn't clear in my question, but could you go back a few slides? I think it was the Geiss result. I'll say stop when necessary.
Oh, yes. Now yes. You're talking about this one.
Yes, exactly. So electron temperature.
Yes.
So I understand that I agree the decrease has got to be the adiabatic expansion. Of course, there's no axis, there's no scale on the axis, but
yeah. Now it is the coronal temperature goes up. Look how these overlap. Whether this goes up very steeply or so gradually here, that's just the transition from the solar chromosphere into the corona. Now, I don't say that this is a moderate increase like depicted here. It could be steeper. Look at the regions where these ions freeze in. All I'm saying is that carbon is probably slightly closer to the sun where it freezes in, and silicon is higher, but that's not a very hard prediction here. It could be a steep, almost vertical up and then going down.
Okay, I think the confusion was because there's no numbers on the axis along the bottom, and so it was not clear what distance that corresponds to.
Johannes forbade me to put numbers there.
Okay. No, questions are lining up. So let's stay at the mic, for a little. Hans Zinnecker is the next to ask a question. Could you open the mic, please, and then speak?
Maybe Saliba needs to open his mic. I'm not sure.
I did already. Hans, could you please unmute your microphone?
Can you hear me?
Yeah.
Yeah, now we can hear you.
Yeah. Well, first of all, thanks for a very exciting talk. And also, I would like to congratulate Issy for this very interesting series.
Thank you, Hans.
Here's my question. Comes back to a question I'd asked before, but yet again, I still am puzzled a little bit how you transform an equatorial orbit into a polar orbit. There must be some torques. I mean, you change the angular momentum of the spacecraft. So how does Jupiter do that?
Oh, once you approach Jupiter, you can approach it from different directions. If, like solar orbiter, you just want to become faster, you sneak up from behind and Jupiter pulls you a little bit and makes you faster. If you want to slow down, like Parker Solar Probe wants, in order to lower the perihelion, you sneak up from, you let Jupiter pull up behind you, and your orbital velocity is lowered. Now, for deflecting the orbit, all you need to do is fly over the poles of Jupiter. We flew you essentially over the North Pole of Jupiter, and we were deflected south. That's all, and the rest is JPL mission operations.
Okay, so it's just aiming at a particular impact parameter.
Aim at a particular impact parameter, precisely.
Okay. Thank you very much.
Thank you.
Okay. Ashwand is the next, on the list of.
Marcos.
I don't know. I just read Ashwand here. I'm sorry.
Okay, do you hear me?
Marcos. Hi, Marcos.
Hi, Rudy. I have a comment to this temperature increase in the lower corona. Yes. I think this is just the hydrostatic scale height weighting bias. If you have a 1 million degree plasma, you have a scale height of 50,000 kilometers. And then if you go to 2, then it's the double, it goes linear. So that explains the temperature increase, what Lindsay asked.
Oh, thank you. Thank you, Hans. You put it nicely.
Okay, thank you very much, and apologies for missing the first name. Youth Hudson has a question. Thanks for the history. A small question is the isothermally of iron, which you emphasized, consistent with Coulomb collision theory?
I think yes. In the science paper, we have given the ionization recombination rates with the ambient coronal electrons, and it looks like they are sufficiently similar that it is meaningful to speak of isothermal corona. But of course, each pair of iron ions can be converted to a temperature, and these temperatures could be slightly different. But I think that's as close as they can be, and in that sense, I think we were entitled to speak of of, here it was, of a sufficiently isothermal corona. I think the collisions with its ionization recombination with the ambient hot electrons. Yes.
Marcus, did you have a follow-up question? Yes, your hand is still raised, or is that a leftover, so to speak? Okay, so no question. I'll go back to the chat channel. Nariaki Nita asks, is there a consensus as to the origin of helium-3 at the galactic nuclei? It is still elusive in solar energetic particles. Or it is still elusive in solar energetic particles.
Oh, helium-3 and solar energetic particles is a very different and very difficult thing. I think the answer is, as far as I know, yes, there is a consensus about the helium-3 from the interstellar medium. I haven't followed the IBEX mission on that issue, but from Ulysses, I think it's as clear as can be. By the way, I should have said, the helium-3 we see on Ulysses is not directly the helium-3, the primordial helium-3, because the helium-3 we see from the sun is the sum of deuterium and helium-3, the sum of primordial deuterium and primordial helium-3, because when the sun forms, all deuterium gets burned up. The deuterium has binding energy of 2 MeV, a little more. So it gets burned up. There is no deuterium, no primordial deuterium in the sun. It's all been burned in helium-3, so it's the sum of the two. But okay. Yes, I think that's a consensus.
Sorry. Oh, Chai Wang asks, what's the difference in composition such as O7 between ICME and background solar wind?
The ICMEs are hotter than the background solar wind, so there is more O7 and sometimes even O8 in ICMEs than in the background solar wind. And there is much less or almost none in the fast streams from polar coronal because they are so much cooler.
There is another maybe related question by Steen Harland, who asks, first thing, he says, thanks for the nice talk. And then he asks, I'm a bit surprised by the O6 plus versus O7 plus abundance. Any idea why, any idea why there is a preference for O6 plus? Does charge exchange take place in the solar wind?
No, the charges, O6 plus, O7 plus, those are frozen in. Once they have lost equilibrium with the hot ambient coronal electrons, they are frozen in. That's why we call them freezing in temperatures. And they are frozen in at the point of last contact with the hot electrons. That's why they are messengers of the coronal temperatures once you observe them at 1 or 5 or 50 AU. O6 plus is simply more abundant because of the the coronal temperature. If O7 plus were more abundant, the coronal temperature would have to have an excess of 2 or 2.5 million degrees. O7 plus, by the way, is a single electron atom and a single electron ion, and it is very quickly then further ionized to O8 plus. It's almost a transitionary charge state, whereas O6 plus is a helium-like atom and fairly stable. That's why O6 plus is almost always the dominant charge state of the heavy ions.
Okay, I have 2 more comments, actually. I mean, the first by Jean-Luc Chausset. He says that he was at the ESA Space Science Department in 1990 and got a chance to see the Ulysses spacecraft and the launch with Richard Marston, who we all know very well at ICI, and look at to the Ulysses Jupiter flyby at that time. Great souvenir for a great mission. Congratulations for the presentation and the results.
Thank you very much. I was also at the Jupiter flyby, and maybe we have met there. But yes, these were exciting times. And by the way, here's a Ulysses, so everybody can have a look at Ulysses, but it's not quite the real one. And actually, it's not Ulysses, but it's ISPM, as you can show.
Okay. And James Connell says, good talk. Speaking of staying on during power sharing, COSPN was kept on to prevent the hydrazine from freezing.
Yeah, exactly. That's one of those. COSPIN had to be kept on because had it been switched off, compensation heater would have had to be switched on, which would have used more power. That's why COSPIN, and the same applies to SWIX, had to be kept on at all times.
Okay, thank you very much. This is exhausts the comments in the chat channel, and I see no raised hand anymore. So thank you very much, Rudy. Thank you very much for attending this seminar. As I said in my intro, we will pause next week, and then on November 5th, start the astrophysics astronomy part of the Game Changers seminar series. And the first talk will be by Enrico Bosso on integral. So I'm looking forward, to seeing you all again. And I think Maurizio or Joachim will then be your host at this part of the seminar series. Thank you very much, and have a good day. Bye-bye.
Bye, everybody.
Bye, Rudy. Thank you very much.
Bye, Danke.